Hi, this question is about the wedge, which is balanced from the middle, right? From its middle. But remember one thing, the mass of the wedge is not uniformly distributed over an axis, right? So, for example, if I assume this is an axis, so the minimum mass is located over here, whereas the maximum mass is located on this part. So, if you place a cylinder of mass small m, right? And we assume that it is balanced, it is perfectly balanced from the middle at the distance L by 2, then what we need to calculate? We need to calculate the ratio of the mass of the wedge and the mass of the cylinder. Now, when I say it is balanced, so it means that it is in a rotational equilibrium, right? I'm basically giving you the idea that how you should proceed, how you should solve this question, right? I'm giving you the map of the question. So it means that sum of all torques is equal to zero. Now in this diagram, we see that there are the two masses, right? The one is a mass m, and we should this is a mg. This is a force that is trying to rotate this wedge in this direction clockwise. Now, this clockwise torque must be countered with another with a counterclockwise torque. That means that that must be produced by the mass. So mass of the wedge. So it means that the weight of the wedge. So it means that the point, the center of the mass must be located on the other side of this pivot point. So this is in the middle. This is our pivot point. Okay. So, dear students, it means that the torque produced by this distance is L by 2. The torque produced by the this cylinder must be equals to the torque produced by the mass of the wedge, the weight multiplied by G, that is the weight of the wedge, times the center of the mass of the wedge, right? Right now, we don't know where the center of the mass of the wedge lies, but let's assume this point is somewhere here at this point, okay? But we will try to find it. So I hope you get an idea that how should we proceed. So right now our target is to calculate the 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 center of the mass of the wedge. But how can you calculate it? You have to first calculate what is the total mass of the wedge. So now in order to calculate the mass of the wedge, I am assuming that this is our reference point. This is our origin, okay? So it's our initial position. And you notice one thing, that the mass is not uniformly distributed. So so what we will do, in a calculus method, we will apply integral in order to calculate the total mass. But what is the mass distribution? The mass distribution is given by this factor lambda, that is a linear mass density. It is the total mass divided by the total length, which in order to show, let me show you that. For example, if I take a small patch which have a mass dm and it has a length dx, right? So lambda can also be written as like this. So dm, differential of mass, can be written as mass density and times dx. Why we need to show it like this? Because, dear students, what we are trying to do, I told you that we have to find the total mass. In order to find the total mass, you must apply integral of dm starting from the zero, which is this point, to the upper limit, that is L, at that end. So let's apply. So here I will write from 0 to L, and the differential of mass can be written as lambda dx. Now, this will give us the total mass of the wedge. And then second step will be to find out the center of mass of the wedge. So this is equals to bx square in a question. B is some appropriate quantity which have appropriate units. So it's basically a constant. So B will come out, and we will apply limit on the x square, and this will be equals to x cube over 3 from 0 to L, and that would be equals to BL cube over 3 minus B into 0 over 3, and that is equals to BL cube over 3 is equal to the total mass of the wedge. So this was our step 1. This is our step 2. And now we are proceeding to the step 3, where we will find out the center of mass. So the center of mass of the wedge, it we have already an equation that dx from 0 to L divided by the total mass, right? And the total mass is obviously m, right? So if we solve it further, so x, and if you remember that here we have dm, so we can place here the lambda times dx divided by the total mass. Okay, basically here we have the integral of the mass, differential of mass from 0 to L, which you already know that this thing will be the total mass of the wedge. So that's why I'm writing it like this. So in the next step, we can place a value of the lambda, right? So it will be okay. So you have already seen something similar, right? So it is now x cubed dx from 0 to L over m. Now this time we will have x raised to power 4 when you will take integral of that. So it will be x raised to power 4 divided by 4. Apply the lower limit 0, upper limit L divided by m, right? Whereas the you know that the m is bl cube over 3. Anyway, so let's solve it. So it is bl raised to power 4 divided by 4 divided by m, which we can write bl cube over 3. And then you would see that it is 3 over 4 times L. Okay, what this is, this result gives us information. So this 3 over 4 L means that the center of the mass of the wedge is from is 3/4 of L, means that this distance this distance is 3 by 4 L from this point. Okay, which proves my point when I said that the larger mass is concentrated on this side because mass is non-uniformly distributed now. So the mass that is on this side is equal to the mass of the rest of the wedge on this side. That's why the torques are equal. Okay, so now we are going to put the value in the step number 1. Yeah, sorry, here is we don't have the x wedge. It's basically the distance of the center of mass of the wedge from the equilibrium position, which is obviously it should be equals to L over 4, right? So I must write here L over 4 and L over 4. So then you can solve it. If you multiply 4 on both sides and you divide small m on the other side, so you would get 4 over 2, and that is equals to 2. So the right answer for this question is